Following some comments from our first week's study, I decided to use real-life datasets for our in-class demonstration of the algorithms, which is more motivating, and when you have more meaning to the dataset, to the data, it might be easier to understand the algorithms. But then I found that the capability of finding example datasets to experiment data mining machine learning algorithms itself is a capability I think is helpful to students and worthy talking about. Um, okay, that is not a general case when you apply data analytics in work in real life, because then you probably have an existing project into which you are about to design your algorithms or models. But when it comes to study, it is useful to find some data or some meaning of the project uh, as a good beginning, as a good start. Look, if we Google machine learning datasets, okay, which is a popular Google term, and I think this way we can find some central repository of the dataset. The two mostly useful one is the UCI machine learning repository, which has more than 1 decade history and has perhaps tens of thousands dataset available in this repository. And another useful one, perhaps people have attended the introductory data analysis have already know about that. It's called Kaggle. Kaggle is a website that's hosting datasets which has been useful for hosting contests. Like you have the data, you have the objective of what information is to be predicted from this data. Do you want to find the best algorithms? You can publish your data on Kaggle and let people to compete to build the best models. You can even put a prize to award the best team. Now this Kaggle is very popular. Look, the advantage of finding datasets using this central repository is generally either Kaggle or UCI. They have explicit guidelines for the authors of their datasets. So each of these sets are generally organized satisfactorily, or at least you have some instructions on how to deal with the data. For example, the very famous IRIS dataset is from UCI, and if we click this dataset here, you will find a basic description of the data, and the number of instances, of course, and the number of attributes, which are the two most important aspect of the dataset. And this also has some area what the dataset is about. For example, if you are in some biology major and you come here to learn data analytics skills to apply to your field, although you may not have a particular project in hand, but you can at least find something that in your area to experiment about. And it has a description of the dataset. Also, the meaning of the attribute, of course, that's only available. This is only available when the number of attributes is few. And some relevant papers, which is very useful because if you do not know how to deal with the data, you can always check the paper. And on Kaggle, of course, it also has such and such attributes, which you might find useful. Especially, I think they have examples like the famous Titanic dataset is from Kaggle. Also, if you enter Kaggle from another, yes, if you go to kaggle.com instead of kaggle.com/datasets, it contains very useful examples such as, look, this is a Python data visualization, and look, genetic data analysis, stuff like that. So have a good explore. Let us use the Iris dataset. If we go to the data folder, have this list file, and if we use this iris.data, click it, we have different choices. We can either try to save this file as, or we can click it, have a look at the data itself. It is a pure text form, so as we have done in the first week's handwritten data, we can just copy all and select all, copy them, and paste it as plain text. Here we have to make a point that for those text data, we need to use a plain text editor to save the data as a plain text format. We cannot use editors like Word or on a Mac computer, Pages or OpenOffice. Those are formatted file, text file. It will contain the font and other stuff instead of only those data. A very useful text editor is I'd like to use is called Sublime Text. Let's copy the data here and save it. So I will save it to the same working directory of our notebook. Call it iris.text. Okay, save. Okay, I already have this one. Now let's choose replace. Now let us investigate the data a little bit. Those are comma separated data. Obviously, the first 4 columns of each data sample correspond to the attributes of the sample, and the meaning of the attributes has been stated in the data set. Check. They are the look, those different measurements of the flower. Okay, and look at the data. The last column represents the prediction target, which is the species of the flower. Right. Now let's close the data, and we will try to use Python to load those data. Okay. We'll create a new notebook in the working directory. As usual, use the first cell to state something like load and pre-process the data. So as usual, let's import the necessary libraries, which is NumPy here. Okay. Let us try to load the data first. Load the data directly. Remember, we have generic NumPy array. Use the gen from text function. Let's try this. data nappy.gene from text. The file name is iris.txt. Note that in Python, you have both choices of using single quote or double quote to represent a string. Let's simply execute, run this cell, see what will happen. Okay, let's check our data. Oh, doesn't seem to be okay, because of course we have 150 samples, but we assume each sample should have some attributes. But now it looks like each sample has been loaded into some single object. Check the one single sample. Well, that is non-defined value, so which cannot be right. I think the probable reason for this is that because the data consists of both numbers and strings, so this function cannot interpret data correctly. After Google a little bit, actually, I find that this function of NumPy is useful because the function allows you both specify the delimiter, which means the character used to separate different attributes of a data sample. Delimiter equals, now we have the comma, and how many columns you are going to read from the file. Use columns. We have 4 attributes, and we can specify the format of the data. Okay, type. Let's check. Now we can specify the data type. Let this to be nappy.float number, which means real number actually. We call them data x. So execute this cell. Oh, there's some. Oh, the reason for this is it tries to find the columns to read, but I specify the number of columns I want the function to read, but actually it wants we to elaborately list the indexes of all the columns we wanted to read. That is to be, for 4 columns, we want to list 0, 1, 2, 3. That are the first 4 columns. If you notice, I use a pair of parentheses instead of a pair of brackets here to specify a list. Actually, for many uses, a pair of parentheses has equivalent meaning as specify a list that is an ordered set of objects as the bracket. The difference is that in Python, if a list has been specified using a bracket, you have the freedom of adding or deleting element to or from the list later. But for a list specified the pair of parentheses, it must be a constant list. It has to be fixed without being able to modify it. Okay. Anyway, let us read the data. Okay, have a check. Print data x. Oh, I have printed. Oh, it looks okay, but actually I was about to print its shape. Now we have 150 samples, and each sample contains 4 attributes, and each sample represents a specific iris flower, and the task is to predict the species of this flower. Okay, Next step is, of course, to read the target value of this dataset. We use the same function, just instead of read the first 4 columns, we let it to read the last column, that is the name of the species. Okay. Columns 4. Note, if you use a pair of parentheses instead of a pair of brackets to represent a list, and the list contains only one element, you need this comma to distinguish that this is a parenthesis specified list, or in our terms it's called a tuple, instead of the number 4 has been happened to be enclosed by a pair of parentheses. Okay, please notice this little language specification to avoid unnecessary errors. Okay, let us run this cell. Oh, we got some problem. Yeah, of course, because I forgot to adjust the data type. I assume many of you, when you try to follow the example, you may find the same problem if you do not pay attention enough. The last column, instead of to be a float number, they are strings, right? The string type in Python is called str, obviously. Okay, let us have a look at the data y. Because they are strings, I'd like to print a few examples of y. For example, the first sample. Assumably, it should have 150 samples. Okay, let's print is 100 sample, and the last one. Say what we get. Oh, seems to be reasonable values, and if we print all of them, could be a little bit messy. The first few tens of flowers are of the same species, and then followed by another species, and then the last species. There are 3 species together. Okay, let's delete this cell. It's to be it's a little bit messy. The next step is to process the data a little bit for the observations, which I call data X part, the attributes. The 150 by 4 array is enough for us to process, but for the target value, there are 3 different strings, which could be a little bit tricky to handle mathematically. Okay, one way to do it is first let us to summarize how many classes we have from this collection of class memberships. The function to do this is okay. Let's consider not the name of the function, but the functionality itself. We would like to take all the unique species from the 150 different collection of different species, a collection of species. Those unique members of an array could be collected by NumPy using NumPy dots, not surprisingly, unique. Yes, and if we provide unique, the array or the list or the data matrix, depending on the terms you call it, it will return you the unique possible values of this array. We run this. Okay, we get 3 unique values as expected. Now we can convert the strings in this array into three different numeric values according to whether they are identical to each of these class names. Let us give those unique values to a variable, call it classes equals unique data y. Okay. Now, the obvious thing to do is we for each y in data y, for each of the data sample, we compare it to the members in the three members in the classes. If note the underscore sometimes, or it is a convention by some people, including me, use underscore to represent temporary variables in Python. That means I use this for each element in data y, and this each element I do not want to specify it each time. I just call it y score. So in the following argument or statement, I use this y underscore to represent each element in data y. But other than those for loop, the y underscore is meaningless. So that is a temporary variable. So if y underscore equals the first class is 0, what we want to do? We want this data sample to be the first class. Let's call it perhaps numerical y. The numerical y should be an array of the same length of the data y, because for each element in data y there will be an element in numerical y. So let us first give numerical y, let numerical y to be an empty list, and then let the empty list append an element. So let it to be 0. Okay. If it is not 0, the next step is to compare if it is belonging to the second class. It's called else if class is 1. Should be indented correctly. Please note that Python is a very stylish language. It forces you to write code in a good style. If you do not indent your code correctly, the logic of the code could not be interpreted correctly. It interpreted the relationship between code blocks according to the indentation. So keep this in mind. Indentation is important in Python. So if it belongs to the first class, this numerical y need to be appended by an element 1. And otherwise, we should append element 0 to it. Append element 2 to the list. Notice that when we write Python and we write the column at the end of the for loop or if statement represent the relationship between code blocks. So if you want something to be evaluated and according to the evaluation and do some processing, you need this column sample at the end of your if statement, the same at the end of a for statement. the same as the else subclause. So that is important, otherwise you will encounter an error. Let's try to run this cell. Okay, now let us have a look what y we get. That seems to be reasonable. 111,222. That is good. Okay. Just one more thing to explain. We are going to use a tool for us to build data models, to build neural network data models. And actually, many model building tools allows us to specify the class membership using integers like this. Or even some sophisticated or convenient tools allows us directly use the string class labels. But keep in mind that internally, these tools will convert labels like this into a label code. Let me explain the label code a little bit. Consider that if some sample, the true value of sample, let us call it true value 1. If using this representation of the classes, let the true value to be 0, and consider the prediction 1. Let it to be 1. And what is the error in this case? Perhaps we want to say error 1 is the absolute value of the difference between the true value 1 and the prediction 1. Correct? So print error 1. Let us see what we have. As expected, it is 1. But consider that if we have exactly in the exactly same situation, however, instead of predicted this true value, we have the true value 2, but the true value 2 is also equal to 0, and instead of predict the true value as 1, we predict it as 2. So in this case, what will be the error? Oh, sorry, this should be error 2. Now we have the error to be number 2. But consider these two situations. Can you see that the mistake we make by predicting a flower belongs to the class 0 to be belonging to class 1 is less than the error that predicted to be class 2. Consider that the class number just happened to be according to the order they appear in the dataset. It is very arbitrary and it is not principled method. Okay, we cannot see one type of error is more important than the other type. It is mathematically inconsistent. So generally, we'd like to actually use a code to represent those classes. For example, let the true value to be the value of the first class, and the true value is integer 0 belongs to class 0. Well, here is a little bit confusion, but keep remember that in many programming languages, the index start from 0, and 0 means the first. Okay. Instead of explicitly 0, we could have a list which has exactly the same number of elements as the number of classes. So, for example, we have 3 classes. Let the list has 3 elements, and to get the specific class we want this label to represent, turn the value corresponding to that element to be 1. So that means class 1. And for example, in the prediction 1, if the prediction 1 is the second class, we can also make a code like this and have the second element becomes 1. Okay. Now if we want to calculate this element-wise minors between two lists or between two arrays, we need NumPy's help. So let's use NumPy as array to convert these two lists. As expected, if we compare these two lists elementally, we will end up with different in two elements. Okay, so now we need to use NumPy's absolute value because absolute value will be taken between two lists, and this list minus this array minus the other array. Okay, and we will take the summation of this error. Okay, let us first see what the error is. Okay, the error is 110 means there is an error in the first class and there is an error in the second class. Okay, there are discrepancies here. If we print its summation, the total error is to be 2. Okay. If we use the same scheme to represent the second condition, okay, now we will have the prediction to be the second class, and let's consider the summation of the error. It's also 2. Now the two situations become the same. Okay. This representation also has the advantage of allowing you to interpret your prediction more freely or more mathematically reasonable. For example, instead of producing those 0-1 predictions, we might want to predict a real number for each class, and we convert those real numbers in each class in values between 0 and 1, and do a normalization step so that we sum those numbers up and let each element to be divided by this sum, so that the summation of those numbers is exactly 1. Then we can interpret the predictions to be probabilities. For example, when the prediction in this case to be 0.1 and 0.9, that means our predictor has 10% confidence in that this sample belongs to the first class, and has 90% confidence that this sample belongs to the second class. Of course, this is wrong, and I assume the error is still big, but that in this case, error is more mathematically manageable than if you are only allowed to be output 0, 1 black and white predictions. For example, now look, this error is 1.8. If the predictor has a little bit more confidence in the correct class, and a little bit less confidence in the incorrect class, see what the error should be. Look, the error is lower. So this representation makes it also mathematically convenient for us to deal with classification problems, especially multi-class classification problems. After we have done with loading and pre-processing the data, we can now collect our code and organize everything together. Sometimes it's a good idea because, for example, those data processors, that is not the core function of this, the core stuff of this study. we can collect all of the code and put them away in a separate file. Let's have a look. We can call the data y here and copy and paste the classes here. Okay. We can also slightly reload the variable data y to be the processed labels. Let it to be nappy.sArray. Remember that this function converts a normal list into a nappy managed list. That is easier for mathematical operations. Let it to be the numerical values of y. And if you hadn't skipped the previous section of this video, you know that this number y gives you the representation of the classes as 0, 1, and 2. However, internally, the classifier needs to represent those classes in codes in the we call it one hot code. When the class membership is 0, the code is 1, 0, 0. When the class code is 1, the code should be 0, 1, 0. And the last class is represented in this way. And remember that is internally. From the user's interface, we enjoy the convenience of represent classes as 0 or 1 or 2. Now we can collect this piece of code. Let us have our text editor. Remember, we need the plain text editor. Put the code here, and remember to import our nappy, because we use the nappy functions here. And we can save our file in the same working folder, like we call it subroutine. Subroutine is a term means you delegate some function to some other program, so that is a subprogram of the main program called subroutine load data dot Python. In convention, the Python file will call it Python. It is note that is different from the IPython notebook file. Generally, the extension name is IPython notebook. IPython is a short. IPython is abbreviation called for interactive Python, which is before the introduction of Jupyter Notebook. But that is just has some historical significance. We don't need to worry about that. Let's call our file subloaddata.py. Save. Look, my editor is nice enough that if you save the file as Python, it will recognize it and highlight the text using Python's grammar. We can close the file, and we can remove this entire piece of code and replace it with run and run sub load py. Remember, when you try to give argument to some commands, you can hit the tab key, and the notebook environment try to automatically complete the command for you. That applies also to the command to as the magic command as run. If you type half of the file name and click tab, it will automatically complete the file name, which is convenient. Let's try again. Do the kernel and restart and clear output. Now we restart and clear all output. Don't worry about the cells below. Let's run the first two. Import Python. Actually, this is not necessary here because remember in the subload data, we firstly import Python at the beginning. But it does not matter if you re-import a package because Python is smart enough to recognize the duplicate importation and will not do unnecessary copies of package in the memory. This is explicit and easy for us to understand. Okay, this is a run subload data. Okay. Let's check if we have our data x and data y ready. Oh, we have these two variables. Okay, this is the shape of data x and the shape of data y. Seems to be okay. Let's check a few elements. The first 5, remember this means everything, and the full syntax is start, end. The end is exclusive, and step size. Step size by default is 1. And the end now is 5, and the start by default is 0. So that means print out the element indexed by 0, 1, 2, 3, 4. Remember 5 is exclusive. Okay, 0, 1, 2, 3, 4 means 5 elements in data X. Data Y, the first 5 elements. Have a look. Seems to be reasonable. Okay. Now we are ready to build our neural networks.